everyone. This is my talk today, Linux for the Cloud Native Engineer. So a little bit about me. Slides are working, that's good. I'm the head of research at a company called Adera. We build what we call a hardened runtime for containers. And basically what this means is that we work kind of a layer below the operating system kernel, and we develop kind of what we call a cloud native hypervisor. So it's a hypervisor. Yeah, so we develop a hypervisor that can run Kubernetes containers, so you get all the kind of performance benefits, all the usability benefits of containers with the isolation benefits of a VM. And one of the things that I've really learned while working there that will kind of learn why I say this all in my intro is that the whole stack really matters, right? Even if all you're doing is developing an application that's going to sit inside a container, where that application is can't actually matter, and you'll see things that affect the performance, affect the usability of your container all the way throughout the stack. And so that's kind of the inspiration for this talk. Also very active in the CNCF community. I'm one of the co-chairs of CNCF Tag Security and Compliance, which is a lot of acronyms for just a group of people who care a lot about the security of the cloud data ecosystems and making projects in the CNCF more secure. Also a maintainer of the Update Framework, or TUF, which is a CNCF graduated project, also in the security space. And coming to you from New York City, where I'm very excited about this warm weather today. I know it's normal here, but we've been having a cold winter over there. So excited to be here. So what is an operating system? I think a lot of people will kind of, especially if you work above the operating system layer of the stack, can be a little bit scared of what this actually is. I think the operating system for a lot of people is the thing you install so you can do all that other stuff you want to do, right? Or it's the base image you select before you actually try and write your application. But what does it actually mean? This is one definition from Wikipedia that I kind of like. An operating system is system software that manages computer hardware and software resources and provides common services for computer programs. Now, doesn't that sound a lot like what you do as a platform engineer, right? So I think there's a lot of parallels, and we're gonna get more into that. So if you spend most of your time writing applications or managing cloud infrastructure, you may think that this doesn't matter. Everything that you don't have to care about the operating system, right? It's just a compatibility layer, right? Why does it matter? But under the hood, all the layers that you're used to, the Kubernetes API, Terraform, Prometheus, they actually rely on the operating system to do what you want them to do. So here's a few examples about why you should stay in this room and not go to some other talk. The Kubernetes or Docker or any other container tool, they rely on operating system primitives like namespaces and cgroups to provide resources. And so those are actually pieces in the operating system that you're actually interacting with when you're using these features. Infrastructure as code that you're writing determines access to things like CPUs, things like memory, things like networking. And these are all actually controlled by the operating system, right? Any hardware resource, at the end, you can't actually get access without that being mediated by your operating system. Observability tools that provide things like metrics and tracing that track, these things track not just what happens in user space, but also what's happening on your CPU, right? You might care a lot about CPU utilization and making sure that you're using the resources you're paying for efficiently. And this is also in the purview of your operating system. And that's how those observability tools actually get that information, is through interfaces that the operating system provides. So you may actually be using the operating system without even knowing it. And one source of performance bottlenecks in your container may be the way that memory or CPU is being used by the container, right? That comes back to why do people care about CPU utilization or anything like that? It's because these can be the performance bottlenecks that you have. So for example, one reason this could matter is that knowing the number of threads available to your container from the CPU tells you how many threads you could use without double scheduling. So like talking about threads and CPUs sounds like it's way below the stuff you have to care about, but at the end of the day, if something's slow for some reason and you can't figure out why, this might be why. Or if you've ever seen like a permission denied error when a container is what you think it's running in privileged mode and should be able to do what you want, but this can happen because even though if the container has privileges, it might not actually, the process that the container is in might not have those privileges on kind of the host operating system. And you can get some kind of weird errors in this space as well. And finally, resource utilization, similar to performance. This can kind of come down to how the container is scheduled in the operating system. And all these bugs, I think most people in this room have probably debugged and fixed these bugs totally using user space tools that you're used to. And I think that usually that's what you should be doing. But But I also think that it helps a lot to understand how those tools actually interact with the lower layers, to understand why it works. I'm a big believer that like understanding why stuff works can just make you a better operator wherever you operate. And so yeah, at the end of the day, this whole thing all really is connected. And so the next thing I want to do is talk a bit about the history of containers as kind of a way to talk about how containers interact with the operating system. I think this history kind of shows you, why containers in the Linux operating system are kind of one and the same. So first we have some prehistory. So before we had this idea of a container, people had computers, and they still wanted to run multiple applications or have multiple users of the same machine, especially in the really early days of computers, right? Because they were these big, expensive things, and it didn't make sense to have one just for one person. So you'd have like a university who wanted to share a computer among multiple different people. And so what you do is you make a virtual machine. So basically, to isolate a process, you make a whole new operating system for that process. And what containers did, and we're going to get into this, is they kind of moved this abstraction up the stack to what we call operating system virtualization, or virtualization within the operating system instead of the whole operating system. And the first place that I like to start this history is in 1979. Okay, I'm going to do a quick poll of the room. How many people think it's ch root? And then how many people think it's ch root? I don't know how to It's okay, here, the first one, ch root, raise your hand. I'm going to use it for the talk, so yeah. And then chroot, raise your hand. Okay, we're going chroot. Chroot wins today. So chroot was introduced into Unix in 1979, and it's a command line and system call that changes the apparent root directory for the current process and its children. There's some connection between this command and early uses of the term jailbreak. So if you've ever heard like a container break escape called a jailbreak, this is like the first time that was used was a process that can bypass chroot. This command does not prevent tampering by root and does not prevent a true root user from creating device nodes and mounting other parts of the file system on them. So this is definitely much less comprehensive than containers that we're used to. It only focuses on the file system isolation and not system calls, networking, etc. So then a few years later, in 1999, FreeBSD jail was introduced. This allowed system administrators to partition a FreeBSD system into independent systems, which they call jails. And these are more like virtual machines than today's containers, right? We're kind of making a progression here. Each jail provided an entire virtual environment with its own file system, its own processes, its own user accounts. And there were several limitations of this that were addressed later, like you can't actually mount or unmount file systems to a jail or access device nodes. So they had somewhat limited functionality. But they were developed to separate customer workloads in a way that would be kind of familiar to folks today. Next, in 2004, we had Solaris containers, which was the first one that combined resource controls with boundary separation provided by what they call zones. There's an incredibly confusing naming convention here that I won't go into the whole details, but there's two features called Solaris containers and Solaris zones. When combined, they're either called Solaris containers or Solaris zones, depending on who you ask or when you ask them. So I'm going to call them containers, but yeah. So whatever you call them, they had the ability to assign storage and resources to a container. They did not have a privilege mode. So anything that requires like privileges in an OS, anything that you'd have to like use sudo to do is not possible. But like today's containers, Solaris containers ran on the host operating system and allowed both resource assignment and boundary mechanisms. So we're kind of moving more towards a container-like ecosystem. Next, we have OpenVZ or Open Virtuoso, which lets a server run multiple operating system instances for different users. All guests use the same Linux kernel with separate views on files, users, processes, etc. And this also provided resource management to prevent kind of resource hogging, because you kind of start to have that problem as well as people are using this. Originally, OpenVZ used chroot to share a file system between environments, but later it actually introduced separate kind of file systems per container. An environment can only be granted access to real devices with OpenVZ, and there's some limitations on disk mounts. This was released as patches to the Linux kernel, but it was never like officially merged into the Linux kernel, so it's a bit of a kind of a deviation in our timeline. And now we have one of the big ones, Linux containers, which came out in 2008. This was a year after the release of C groups. And Linux containers combine C groups, which limit and prioritize resources, with namespaces, which provide kind of a separate view of the operating system environment. So mount namespaces were the first namespaces introduced in Linux back in 2002. And then they added several other types of namespaces in 2006 and onward, up until very recently even. And this kind of increased the usefulness of namespaces to the point where a Linux container could then kind of utilize them in this way. And this combination of C groups and namespaces really defines containers today. I think one of the keynotes today even talked about this, where that's kind of what defines your container, right, is C groups and namespaces. And finally, we have libcontainer. So Docker actually originally used Linux containers when it was first released as the container execution driver. But in 2015, they deprecated that in favor of libcontainer, which also uses Linux namespaces and C groups, but also things like capabilities, security profiles, network interfaces. And there was a lot of kind of industry standardization that happened around Docker and libcontainer. And this is when we started to see kind of a whole ecosystem for container management, like all of us here today talking about Kubernetes. And libcontainer was later split into runc and containerd. So it's actually kind of still around. Even if you haven't heard the word libcontainer, you've probably heard of runc or containerd, and so it's still kind of around in the ecosystem. So where do we get? We have operating system virtualization. We have a layer on top of the operating system that uses operating system features like namespaces, C groups, capabilities, everything else there, in order to provide kind of an isolated environment for our programs to run. But underneath all of this operating system virtualization that I just talked about, there's still a whole operating system, and below that there's still a bunch of hardware. So you have your application, and then you have a container runtime, which manages the containers and interacts with the operating system kernel to get access to anything that requires either a system call in the operating system or hardware access to any of these resources down in hardware. So for example, if your application wants to connect to the internet, a packet from your application has to make its way through the container runtime into the kernel, which then sends it onto a NIC, a network interface card, which then passes it to some router or internet connection you have, and then it kind of reverses that to get a response. So if your application has trouble connecting to the internet, it really could be any of that stuff that goes wrong, right? And it's probably very rarely even the very topmost layer is that it's the only thing that goes wrong. And so I want to go through kind of a few specifics of stuff that's going on at the operating system level that you can interact with directly from the container, but also like a lot that happens that's not directly viewable, but still impacts your kind of everything you do every day. So the first one is devices. These are hardware components that the operating system interacts with. I think one that folks might be most familiar with is block devices. You can actually see block devices in a container if you go to this particular directory /proc/partitions. And you can see devices, even devices not assigned to your container, but on the same operating system, even if you don't have permission to access them. And this can be kind of really interesting way to kind of get info about what's happening on your broader system, because you can see, you can just kind of see what devices and which partitions are around. And this is a little bit depending on your memory settings, your permission settings and all of that, but anyway. System calls is the next one. System calls are how users request services from the operating system. Basically, anything a program does requires system calls. If it wants to do anything more than like do a while loop printing numbers or something like that, you often have to use some system calls. These are used for things like process control, management of files, devices, memory, or communication with anything else, like networking or anything like that. And all system calls run in the operating system. And this is true even with user namespaces that let you run more privileged system calls in the kernel as user. Because at the end of the day, the container, because it's on top of the operating system, it doesn't actually have permission to access anything in hardware, including your RAM, et cetera, without requesting that from the operating system. And so this is, I think, one of the big ways that people interact with their operating system. And especially if you're writing lower level programming languages, right, you'll often kind of call things that basically directly call a system call. Like if you write like read file or something like that, you're basically directly interacting with a system call. And next we have processes. The operating system creates all processes and kind of schedules them. And so scheduling between containers on the operating system, containers are a lot like processes. They have obviously all these special properties, but at the end of the day, they do have to be scheduled as processes on the operating system so that they can be scheduled in the CPU or GPU or whatever other processing unit that you have. And there's also, and they also allocate memory to those processes. And so any kind of noisy neighbor attacks, anything where you're worried about the resource usage of your containers, it often comes down to how the operating system is scheduling your container as a process and having that interact with the other resources that it needs. Speaking of resources, next up we have resources. So this is the CPU and memory are probably the biggest ones that come up often in the container world. And you can actually view full resource usage from your container. So you can look at the CPU and mem info from inside a container, kind of see what's going on here, which I think is kind of interesting. Or you can do this on your host system too, and see again like where the CPU is actually going. And this is usually what's used by observability tools on the back end to kind of get this information, but you can see it yourself too, which I think is very cool. So if your observability goes down, you can actually still do this. So in summary, containers run like processes in your operating system kernel. There are things like namespaces, cgroups, capabilities, etc., that are all actually features of Linux that you use every day when you're using your containers. And the operating system manages all the hardware resources, anything like, and basically all the resources in general that your container needs. And so this is kind of my pitch to you, that it's useful to help understand the operating system. Maybe read a book about it, learn more than I can tell you in a 20-minute talk here, and just kind of understand how the operating system works so it can help you understand your containers and help your customers use them better. So thank you. That was me. I think I talked a little fast, so we have time for questions.